areas. Okay.
KGB, watch out. No.
Right. But I'm just going to be setting the scene a little bit and talking a little bit about some of the challenges with PFAS, and we'll hear more from the following speakers about specific challenges as they're being dealt with in regional parts of New South Wales. So I think for me, the first challenge is the name, per and polyfluorinated, or I even left out a word, per and polyfluorinated alkyl substances. If you've ever tried to explain to anybody what PFAS are that doesn't have an honest degree in chemistry, it's a challenge to start to just describe the types of molecules that we're talking about. What is this per and poly business? And so usually you end up resorting to trying to describe what the molecule looks like. That doesn't work now.
Sorry. Scroll down.
Scroll down.
Yeah. Seems to be.
There we go. Scroll up. So challenge number 2 is actually defining what PFAS are, and this is just from a bunch of Google searches I did a week or so ago. I'm looking at, well, how many PFAS chemicals are there? And it doesn't take long to find references to PFAS are a group of over 4,000 chemicals. PFAS are more than 12,000 chemical substances. PFAS consist of at least 5,000 individual substances, over 10,000 highly persistent chemicals. There are more than 12,000 types of PFAS. Growing numbers of PFAS of nearly 15,000 synthetic chemicals. And then there's this study from Environmental Science and Technology saying there's actually 7 million and growing PFAS. So I'm not sure how many chemicals there are.
Control.
Next complication, and a very important complication, is where are PFAS coming from? How are we being exposed to these chemicals? As most people on this webinar will know, that PFAS are in so many different types of consumer products that we can't even get our head around where we're being exposed from. Most of us don't know what our major sources of exposure are, but we know that things like stain-resistant carpets, food and food packaging are very important sources, upholstery, the dust in households because of the carpets and the upholstery that contain PFAS, non-stick cookware, waterproof clothing, and in Australia, very importantly, around some of our most impacted sites are the firefighting foams. So we're all being exposed to PFAS from a variety of sources that we don't even fully understand. Peter? The next question is, so what's a safe level of PFAS? Something that we don't seem to have been able to agree on internationally, and is a moving target. And so we're having constantly changing drinking water guidelines and other environmental exposure guidelines around the world, and differing now by orders of magnitude. There are many countries that don't have any regulatory focus on PFAS in drinking water. They don't yet exist in the WHO drinking water guidelines, or there's work happening in that space. Is shown here some of the guideline values for safe drinking water for PFOA and PFOS in various countries, including Australia. And as we know, we've particularly seen the US through the US EPA maximum contaminant levels move to much more stringent levels, which everybody pays attention to. And so we have people now in Australia saying, well, are American people different to Australian people? Why is a certain level of exposure or a certain drinking water concentration safe in America, but a different concentration is apparently safe in Australia? And that's been a difficult issue to keep up with when you have a moving target and a huge amount of uncertainty around what the actual safe levels of exposure are. One of the big changes that we've seen is when we developed the Australian drinking water guidelines, all of the endpoints, the toxicological endpoints that people were concerned about, were non-cancer endpoints. So we were focused on threshold type toxicity rather than the cancer slope factors, which I'll refer to in a moment. But then in the last 2 or 3 years, we've had some of the big international agencies come out and identify that there looks like there's enough of a balance of evidence to be able to start saying that we think these things may be carcinogenic to humans. And so IARC, the International Association for Research on Cancer, has classified PFOA as carcinogenic to humans, PFAS as possibly carcinogenic to humans. The US EPA says they're both likely to be carcinogenic to humans. But when you actually look at the research, and there's an example shown on the slide here of a recent review, we talk about things being likely and possibly and actually carcinogenic to humans as if we know what we're talking about. But actually, we really don't. There's a huge amount of uncertainty associated with that, and it really is just an assessment of the balance of evidence and the actual evidence for direct understanding of human carcinogenicity from these chemicals is still severely lacking, and there are lots of questions. There are lots of gaps in what we would normally expect in terms of the evidence base to really be confident of such an assessment. So dealing with uncertainty generally means that we need to make conservative assumptions, and that's where we go, and that's what drives drinking water guidelines down. We always err on the side of safety and err on the side of things being potentially worse rather than better than we think they might be. Next slide. Oh, all right. So the way that we've generally developed the Australian drinking water guidelines was consistent to what we saw on the last slide, which is the way that we regulate chemicals for endpoints that are non-cancer based. And so what we call a threshold-based toxicity, the idea is that through animal experiments and sometimes epidemiology, we've been able to identify that there's a safe level of exposure, and below that safe level, there is no appreciable risk to human health. We take the data from those types of experiments, low L's and no L's, and we apply uncertainty factors. And so that's the way that the current Australian drinking water guidelines have been developed, with very large levels of uncertainty incorporated into those calculations by order of magnitude reductions in what's assumed to be a safe level of exposure. But once you change to talking about a cancer endpoint, on the next slide, the model for which we understand cancer toxicity changes significantly, and we start to talk about a model that has a straight line extrapolation for a high level of exposure and a high risk of cancer down to no level of exposure and no risk of cancer, which is on the next slide, if we can get there. Yep, that's the one. So once we start talking about cancer, this becomes the model that we use. It really is a model. No serious toxicologist actually believes that this is an accurate representation of the relationship between dose and cancer risk for chemicals at low dose in the environment. In fact, there are lots of reasons for why we think that low doses are less of a cancer risk than might be anticipated here, and that's because of cell repair mechanisms and other processes. But we use this model to say that the only place where there is no elevated cancer risk is where there is no actual dose or no exposure to this particular chemical. So that's how we get to, on the next slide, should I be doing that? Can I do it, or?
Every time, Peter, that someone in through the into Zoom, an online attendee, he gets control of it again. That's what's causing the problem.
No more attendees. Okay, so that's where we get to this commonly heard refrain about there being no safe level of exposure, and you can find it published many times. The US EPA now believes there's no safe level for these two common contaminants. Not only did the US EPA establish those health effects, they said that based on the best available evidence we have, there is actually no safe level. And this is really a description of the model that's being used, not the actual understanding of exposure to PFAS, but that is the way it gets described as a consequence. I'll try. Oh, there we go. And so when we look at what the US EPA did in terms of how they ended up with their drinking water, their maximum contaminant levels for the two chemicals that they believe were likely to be carcinogenic to humans, PFOA and PFOS, they identify what they call a maximum contaminant level goal. And the maximum contaminant level goal is to have no extra cancer, no cancer risk, and therefore no exposure. So the maximum contaminant level goal for those two chemicals is set at 0. But then the US EPA recognized that, well, you can't measure 0, you can't verify that there's 0 exposure. So we have to be a bit more realistic, and they introduced a second value, the maximum contaminant level, which is for those two chemicals 4 nanograms per litre, at which they say, well, this is the value that's not actually health-based. It doesn't correspond to a particular cancer risk. It corresponds to what they think is achievable and what is measurable using current analytical technology. So it's a very pragmatic number in that sense. And there's a lot of discussion around whether it's pragmatic in terms of cost benefit, but it's really not a health based value. It's a can be done value. Next slide. Good. I'll rush through them a little bit faster because we're obviously losing time. But when we look around the world and we look at how other countries are regulating PFAS, there's no consistency whatsoever. We've got these guidelines that have been recently published through Health Canada. They've set a guideline of 30 nanograms per litre for a sum of 25 different chemicals, including some short chain PFAS. So the first one there is perfluorobutanoic acid, PFBA. As a short chain PFAS is not expected to have the same, not understood to have the same toxicity as some of the longer chain PFASs, yet we just add them all together. So you can exceed the guideline by maybe having a large amount of some of the more toxic or some of the less toxic chemicals. And so there are complications around that particular approach. Another approach from the European Union where they're looking at total PFAS, which means effectively looking at all of the perfluorinated chemicals that might be present, despite the fact that they certainly don't have linearly additive toxicity. Now we see the US EPA backtracking. Some of the 4 of the different chemicals, PFAS chemicals that they had established guidelines for, they're now unwinding, and they look like they won't be going forward with those. And they're looking at longer implementation times for the key PFAS. So this is my last slide, just to say that the complexities around PFAS are such that we know that we're all being exposed through many, many different sources. There was an article in the paper last week, I think, or the week before, from the Australian Bureau of Statistics, showing that about 98% of Australians have measurable levels of PFAS in their blood. This is my data here. I've got about 6 nanograms per milligram of nanograms per microliter of PFAS in my own blood. It's not very comforting to think of, but we don't know what it means. So we know that it's not great. We know that my great-grandparents and all of them before did not have this chemical contaminant in their bodies, but we don't actually have a good understanding of how to actually interpret that in terms of risks of adverse health outcomes in the future. So all of these things make it very difficult, I think, for water utilities and others to be communicating with customers and with the community and try and give a realistic understanding of what the risks are associated with PFAS exposure.
Great.
Thank you.
Awesome. Thank you. Thank you, Stuart, and thank you for powering through despite the technological issues. And thank you to everyone in the room and everyone online for getting through all the technological issues. So the next person we've got is Jason Ip. So, don't worry, Jason, I've got to read your bio as well. You don't get out of it. I can bring it up. You guys can hear my mumbling, can't you? Yeah. Okay, I'll make sure I don't mumble anything too insulting. Jason Ip is the Manager of Operations at Riverina Water County Council, based in Wagga Wagga, Regional New South Wales. He's worked in the New South Wales local government water utility industry for over 25 years, specialising in the treatment, production, delivery of potable water to both urban and rural townships and communities. He's an active participant on the New South Wales Water Directorate Executive Committee for over 10 consecutive years, assisting local government utilities in technical issues, policies, legislative reviews, training, and knowledge of transfer challenges. Take it away, Jason.
Thanks, Trevor. Firstly, I wish to say thank you to the team at the AWA for organising tonight the New South Wales Regional Water Champions event, and the opportunity for River Into Water to share our experiences on our journey with PFAS, which began in 2017 when the Defence Force, namely associated with the RAF base, knocked down our door and invited us to be involved with the stakeholder engagement. And I'm just wondering, Peter, whether you can give me control.
Click on the screen, scroll down.
Okay, thank you. So I'm trying to run through a number of slides, but that's what I'm hoping to address tonight. And I'll be focusing on the three areas that we are experiencing PFAS in Wagga, which is our East Bore Field and our West Bore Field, and also just recently, like as of October last year, where New South Wales Health did the screening exercise of a number of treated suppliers in New South Wales, Tarcutta, where we're one of four water supply systems that are experiencing PFAS above the proposed limits. Sorry, just bearing with the delay, I'm sorry. Okay, just firstly, River Into Water is a county council established in 1938 under the Local Government Act. We cover a big chunk of New South Wales, about 15,500 square kilometres. And our source works still to this today, from 1938, still remains predominantly in Wagga Wagga. And just a few rundown of facts. We've got 29 bores, 3 river intakes, 18 treatment plants, 80 reservoirs and various storages, 36 pump stations, and just under 2,000 kilometres of pipeline. We serve about 33,000 connections. About most of those, 95%, are in Wagga Wagga. And our annual demands is between 15 to 17 gigalitres a year. And as I said before, 90% of that is sourced from our Wagga headworks. What we kicked off with in 2017 is a PFAS response matrix, and this is a very basic framework that has helped us guide and also explain to our stakeholders, our councillors, our board, of how we approach the issues of PFAS as it emerges. And it's basically, it's written in today's speak. So there's a bit of cross language of proposed limits and current limits, and all this gets reset, I understand, in the next couple of weeks. And I've color coded them just to highlight some of the next couple of slides. Basically it works on dilution of the sources, then dilution of treated water to achieve below PFAS limits. Then you start to isolate, and then you start mucking around with demand management, and you look at alternative supplies. And that's an escalation process. This framework has really helped us in a lot of ways of just demonstrating to the regulators of how we are managing the risks. Our system, I'll have to just bear with me because I need to explain a bit of our system so you understand some of our response methodologies. There are 4 predominant integrated systems that are interconnected, and they are supplied by a number of water treatment plants that have the means to pump to the various systems. From Wagga, serving North Wagga and Wagga, North Wagga water treatment plant, just serving North Wagga. It gets quite confusing, and it's always fun trying to explain this to our regulators each time we do our IWCM, our strategic planning. That's our our southern trunk, and this is our western trunk, and all that is connected. It's saved our bacon over the decades of when we have contingencies of power outages, mains bursts, and so forth. Now, I'll just point out each of these treatment plants have various sources, and just waiting for it. Here we are. Okay, this is what everyone's waiting for. This is our heat map. And you can see very quickly that 80 megs a day, 30 megs a day. So you're looking at, and this is all clustered around the Wagga water treatment plants. That's a big chunk of our source waters affected, which predominantly supplies our system. And saying that too, we supply 7 independent villages, such as Tarcutta, and that's our heat map of Tarcutta. Now, Wagga, I hope this is legible from your end. And the river is flowing from right to left. We've got the RAF base about 10 kilometres outside the centre of the urban area of Wagga Wagga. We've got the Gumley Swamp in the intervening land. And then we have our East Wagga Borefield, North Wagga Borefield on the other side of the river. And then we have our West Wagga Borefield. And just to run it through quickly, 2 of our West Wagga Borefields, which is pretty much sort of downstream, so to speak, of the urban area, is twice the limit of PFAS. And with our East Wagga Borefield, and that's generally is of interest because that's the one that has the most sort of famous element to it, because that's the one is at risk with the pollution caused by the RAF base. Sorry, just trying to get the next slide. Okay, that just shows you a bit of an elevation details, that the RAF base is on a bit of a plateau. It drains down to the swamp. That drainage down to the swamp is the predominant pathway from the contamination of the RAF base into the groundwater. And then from the swamp, it goes into the 2 different formations in the alluvials, which is the Cara, which is the shallow one, and you got the Lachlan one, which I'll speak to a bit later. You can see the bit of constriction in the floodplain, and it actually constricts further downstream. Just relatively recent, you got the Kampuka Army Base that's been identified as another source of PFAS. But we are comfortable that that is not contributing to any risks in our groundwater sources for drinking water. But certainly it's causing a bit of headache for those communities that are directly impacted by it. That's just a geological map of the area. It shows the alluvials, and it shows the bit of the drainage network. And you can see from the RAF base draining into the Gumley Swamp, and then you have a drainage system, surface drainage system that heads to the lake. And in relation to our East Wagga Borefield and also a West Wagga Borefield, I've just included these sentinel bores for future discussion because they are of interest. Now, with the testing done by the Defence, this is the surface water results map. This is all publicly available information from the RAF website, and it plots where the orange triangles are. They're above the current guidelines of 0.7 nanograms per litre. And this is the Gumley Swamp area, and this area is the RAF base. Again, our bore field is located about here. This here is, like I said, there's 2 groundwater formations. There's the Cara formation, which is the shallower one, and there's Lachlan. And already in the shallow formation, there is a result that is above the current drinking water guidelines. And the Lachlan one is of more interest because our groundwater bores are in the deep aquifer in the Lachlan, and already we see that the PFAS is detected greater than the drinking water guidelines, the current drinking water guidelines, in the swamp area near this Murray Cod hatchery area. So what the defence have done, they have generated a computer model. This is a pretty snazzy pictorial of that, which shows the Lachlan Formation, the Carra. It shows the Gumley Swamp, and this model was supposed to predict when the PFAS is going to be in the area of influence of our bore field. It's based on particle trace. So there's no sort of degradation as the particles travel through the model, but it's just an illustrative example to give us some guidance of when it is going to be impacted with the closest bore. And I mentioned about the sentinel bores earlier on. Okay, now this sentinel bore down here was originally installed as part of the management plan. It's supposed to be outside the plume of PFAS contamination. Soon after drilling it, they sampled it and realised it had PFAS in it. So there goes all their modelling. And they resulted into installing 2 more sentinel bores slightly down the hill. I lovingly call them canary bores. And even this bore here is only 650 metres away from our nearest bore. And soon after drilling that, yes, they found PFAS. They found it in the deeper Carra or shallower Lachlan. And they've just drilled another bore, another canary bore, closer to our nearest bore, and I'm still waiting for the results of that. Now, these are the results of our East Wagga bore field PFAS for the proposed limits. The one to watch out for is the red. That's the PFOS. And thankfully, we have detected PFAS, generically speaking, and you notice that we only detected it recently. And it's only late last year that we changed our detection regime to be a lower tolerance in line with the proposed limits. And I think a lot of utilities in the state, where they have been doing some prior testing, have to do this particular reset in terms of benchmarking their data. And that is an area that I'll just highlight of what we're facing now. So in terms of the East Wagga bore field, it has a heightened risk of PFAS contamination from the RAF base. We're starting to see something. There's no guarantee that's even from the RAF base, I have to admit. But we're expecting it, knowing that we have a canary bore or two within 600 metres that has detected PFAS in the formations of Lachlan, where we are drawing from. They're the sort of dot points that we are working on plans. Okay, the biggest one, we are benchmarking. We're doing monthly sampling to see over time where it's increasing or decreasing. We're also looking at the fact that we're below the current PFAS limits is our saving grace, so it's all business as usual. But we are looking ahead of working at contingency plans with the Defence to what funding they can assist us with for any modifications to our works. But also currently we are modifying with the assistance of DECU the water sharing plan for the Murrumbidgee regulated to have this special purpose access licence. So when we lose our ability to pump groundwater from our East Wagga bore fields, we can make up the difference, at least in terms of water entitlements, from the river. The West Wagga bore field, just very quickly, you can see located on the urban fringe. We have the other 2 bores unaffected. In terms of managing the dilution of that bore field to below proposed limits, we lose about 25% production. And very short slide, PFAS source unknown. With our operations, we are like an irrigator. We're licensed with water entitlements to extract. We don't look after the catchments. We rely on DECU, EPA, and our constituent councils, such as Wagga Wagga City Council, to do that sort of catchment management regime. That investigation is still underway. And those 2 bores are above the proposed limits about twice in terms of PFOS. What's interesting here, you can see in terms of our West Wagga bore 4, those two bores, they are, look at the red lines, about twice over the 0.004 micrograms per litre. Nanograms, micrograms, I'm sorry. Okay. And you can see here there's been no detection of West Wagga bore 5, but when we started to test at those lower detection limits, yes, it's there. And so that's a readjustment we're currently experiencing. And in terms of our contingencies, well, on those previous slide when I showed you how our system was put together, our West Wagga water treatment plant is the only source of water really that goes down the southern trunk, and it's based on groundwater. We are looking at the contingency of extra pumps and pipelines to convey treated surface water into the southern trunk to offer a bit more resilience for the future. Now, Takata Township. New South Wales Health did that screening test in October last year, and it picked up that Bungendore, Narrabri, Takata, and Warialda were above the proposed limits. And we identified that our two bores, one of which was 4 times over the PFAS limit of bore 5, and our bore 4 at the time was about 1.5 early this year, but it's not detectable. And I think that's attributed to the change in catchment saturation levels with rain, and it's not drawing the contaminated water that's coming from the urban area of Takata. I'll just highlight this potential transport for New South Wales bore because that's 90 metres deep. That's in a different formation. That's diffracted rock compared to our 38-metre bores that's in the alluvials. And that just probably highlights the situation for Takata bore 5, getting up to 16, 4 times over the PFAS limit. And we had that bit of a puff at bore 4. Currently, we've cut over to bore 4 operationally, but I'm expecting when things dry out in the catchment, and that cone influence will get into the similar contaminated water that bore 5 is sitting in. The investigation we've done, we had access to Wagga City Council's urban salinity bores. And again, I'll just run quickly through these numbers. On this side of the old highway, this is the bypass, 6 times over the proposed limit. Opposite the truck parking bay, about 1.5 times over the proposed limit. In the park here, 0.5 times. And in this old school grounds, where this is up the hill, nothing's above it. That had 0.5. And in the table drain in front of our water treatment plant at the lowest part of town, we had 2 times the limit in the table drain. Now that shows you a bit of the formation we're dealing with. So Takata bore 5 is on the edge of the alluvial. It's actually still in the alluvial, but it's more associated with this formation here, which is pretty much the decomposed hillside, sort of layering into the valley on top of the alluvial, but bore 5 is predominantly on the edge of it, and bore 4 is over here, and I believe that when the bore 4 operates, it can pull this water in, depending on the hydrologic conditions. Shows you a bit of the drainage pathways as well. A bit more with that drainage. Just looking at the contours and the drainage plans from City Council's sort of interim maps. You can see a natural drainage path, and that's probably in the cooee of where we got 6 times the limit. So this is sort of indicating where the source is coming from. Again, we don't look after the catchment. We're trying to do our own investigation with some degree of assistance from DECU, Health and EPA. But this is the preliminary investigation that we've come up with to at least point out where the contamination is coming from, confirming things. There's still some more investigation to do. And currently, that's what we're currently doing. We've cut over to the bore 4. We're continuing to develop our baseline data, and it's still early days because this only started in October last year. We are about to commence pumping from the Transport for New South Wales bore there to see whether it's a viable alternative. It has sustainable yield, good water quality. If it passes all those tests, then we can have those discussions about some asset transfer. That'd be the best case scenario that I'm hoping for. Otherwise, we do have the option of a 30K pipeline from Wagga. In terms of other alternative bore sites, we're a bit limited there because slightly upstream from Tarcutta is a piggery. And we don't want to go close to that in the alluvials for obvious reasons. So in summary, this is probably the best way I've found to convey where we're at with our sampling regime. We're looking at the number of samples, we're looking at number of detections of those samples, and number of those detections that are above the proposed limits for PFAS in the 4 constituents. And the only thing to note here is that we only started end of last year, the start of this year, with that lower thresholds of detection. So the results are a bit distorted because previously we had no detection, but now we do. And some of those detections are above the proposed limits. And that's my presentation. Thank you. Back to you, Trevor.
I love when I start speaking and don't take myself off mute. Thank you very much for that, Jason. So we'll kick on to our last presenter, Sally Williamson, who will hopefully talk about some of the solutions to all of the problems we've brought up tonight. So with a background in biotechnology, Sally is an environmental engineer with water quality management expertise spanning over 20 plus years. Her experience has predominantly been in the areas of treatment process planning, design optimization, risk management, auditing, validation, verification, commissioning, the primary focus on enhancing the quality of drinking water and cycled water. Taylor is currently working with Sydney Water, works for Oricon Water. She's got a very long bio because you've done so much, so I'll leave you to start.
Yeah, sorry. Get on with it.
Yeah.
Oh.
There we go.
All right, so just going to
Scroll down.
scrolly.
Sorry.
Or not.
Someone's following me for the screen. Peter, I've lost it. Not mentally, I'm in the screen. There we go.
Let me see if I can just give you control again, Trevor.
Thank you.
Right.
Dictatorship should work.
Do you want to give it a go?
Yeah,
Just
scrolly.
So, Robert, sorry, Richard, you're on the call remotely. You're not on mute.
Yes, I can hear everything. Thanks very much.
No, we can hear you too.
All right. Might as well start here because I can't go back. But as we just heard, my name's Sally Williamson. I'm a process/environmental engineer with Oricon. I do a lot of my work. You might see me working with Sydney Water. So currently my background's in microbiology, as I said, but here I am in this water quality space working with Sydney Water around their PFAS planning for the mountains. But I'm not going to talk about that today. What I've got here is just a bit of a boundary condition around what I can talk about because I've only got 15 minutes and this could, blow out. We could talk for hours around the treatment of PFAS. So I'm not a salesperson. I'm not here to sell anything. I'm going to be completely agnostic when I'm talking treatment technologies. I know there's some vendors in the room and probably on the call, so don't come at me when I don't mention you specifically. I also want to say, there's the other end of the water journey, which is, I guess, biosolids. So we're not talking biosolids tonight, but I guess that's another kind of hot topic in the PFAS management space, which could, have its own session like this, most definitely. You can do it. Click and scroll.
Sorry, Peter. Can you click next?
Yes, lovely. So you've found PFAS in your source water, whether it be the groundwater, whether it be your surface water. So as we've just seen, Jason I mean, data is king, right? So the more you can understand about this, I guess the contaminants, what type of PFAS contaminants you have, where it's coming from, the more chance you've got at actually mitigating that risk. But I guess one of the key challenges is that is cost, right? So it's not a cheap mitigation. You can't mitigate this cheaply. So next slide.
Sorry, just say next really loud.
Yeah. Okay.
Yeah.
So I guess we know that mitigating hazards is the best and the most cost-effective way of doing that is preventing them from happening in the first place. But I guess unfortunately we don't have a time machine. We can't go back in time and say, hey, can you stop using this firefighting foam in our drinking water catchments, please? So that one's out. Next best is, I suppose, oh God, go back. Minimizing the spread. You've got a contamination in your groundwater in the ground. Can you minimize that from further impacting your drinking water source? So yeah, I guess there are some ways you could do that. And if it's too late for that, I guess if you've got PFAS in your drinking water source that's higher than the limits, whatever they may be at any given time, your only option really is to implement some sort of treatment process. So we can go to the next slide. So I did mention, there are ways of potentially minimizing that contamination spread, but I think what I gathered from Jason's presentation just then is that it's easier said than done. So when I put this slide together, I thought, this looks like a perfect solution. Just stop the PFAS from moving anywhere, it's fine. But yeah, it's finding where it's coming from, which I guess is the problem. But there are technologies that, it can help you by sort of ring fencing that plume, if you know where it is. There's technologies which involve injecting colloidal activated carbon into the ground, which sort of acts as almost like a in-the-ground filtration system, whereby the water can still move through, but the PFAS is bound into that colloidal activated carbon, and then you can concentrate on remediating that groundwater plume and sort of minimizing that further contamination of your source water supply. Next slide. When we get to the point where we need to treat it, there's a bunch of options, and this is where I'm going to get super vague, so I'm not going to step on anyone's toes here. When we're talking about separation, the separation of PFAS from the water matrix. So there's, I guess, three main mechanisms. One you'll see often is the binding or the affinity that PFAS molecules have to sort of bubbles, to foam. So what I've got there is a dissolved air flotation system. One such option you could use, which you inject the air, makes bubbles, you skim off the float on the top. Down at the bottom, we've got our membranes. So this mechanism is sort of size exclusion. I think Stuart mentioned long chain, short chain. So there's various sizes, shapes of PFAS molecules. Obviously, the bigger, the more possible that a membrane, a physical barrier, is going to be able to remove. Smaller chains, maybe not so much. But there is, I guess, that physical barrier process there. Then you've got your absorption processes, so things like ion exchange that you see there with the red thing in the middle, and your activated carbon. So activated carbon, you could either have a granular activated carbon contactor, which we've got there. You could potentially use powdered activated carbon, but I guess that's pretty messy and not ideal at the best of times. And I think one thing to note here is that it's really great to understand, as I said, data is king, understanding what the composition is of your PFAS contamination, but then also really needing to understand what the general water quality conditions or characteristics are of that water supply as well, because things like ion exchange and activated carbon, because it's not a physical barrier, you tend to be not super selective for PFAS. So if you're not only removing PFAS, if you're actually removing, your taste and odor compounds, your toxins, your natural organic matter, it means that you're not getting the most cost-effective way of removing that PFAS. And it ends up being a sort of costly operating exercise as you have to keep replenishing your media. I guess another thing that I will mention as well, which I haven't gone to in a lot of detail in this presentation, is because it's another whole level of, a whole big pile of stuff to sort of talk about, is that kind of you've separated the PFAS from your water, you've collected it, and then you've got to do something with it, right? So there's that disposal component. So I guess in itself, there's a whole bunch of different technologies that you could also implement there. I'm not going to go into too much detail on the disposal side, but just noting that the one that's, I guess, most commonly known to work well is incineration, but obviously that's not a great option in terms of how we're trying to minimize our greenhouse gas emissions at the minute. So it's doesn't seem to me like a very sustainable way of doing it. But there are, I guess, some biological, chemical methods of destruction, which are becoming, I guess, more emerging. And I think, as we go along and technologies improve and more research is done, this will be, I guess, a more, a cost-effective way. There will be more cost-effective ways that are more sustainable that we can implement. Go next slide. And then, as I was saying, emerging technologies. So the ones I had on the last slide are the sort of the bread and butter PFAS removal, separation technologies that you might see. But there are most definitely a whole bunch of emerging technologies, and I'm probably not doing it justice. There's probably many others that I haven't even included here. But a few that I've got up here, so foam fractionation. So similar to, I guess, dissolved air flotation, is that kind of banking on that affinity of PFAS molecules to bubbles, to foam. So foam fractionation is, you've got your I guess, bubbles that have different, there's many different, I guess, chemicals that you could enhance the foam formation and make the bubbles more attractive to the PFAS. Bubble it up, foam it out, and then collect it over here, and then you've got to do something with it, as I said. I guess similarly is our electrocoagulation, which I guess a bit more of an emerging technology, which uses that sort of electricity to generate a foam that the PFAS will then bind to. I have also added there the electro oxidation, which is a degradation technology, but I won't go too much into that one because, as I said, I'm not going to speak on the degradation stuff. I've only got 15 minutes, so leave that one for now. And then down the bottom, these are some of the, I guess, emerging research-based resins that we could use. So, as I mentioned, activated carbon, ion exchange resins. Whilst I know there are a lot of different ion exchange resins, and some are more specific to PFAS than others, there are, and there is continuing technological advances, research into other sort of media resins, that sort of thing, that are very specific to PFAS molecules. And I guess the benefit of that, as I mentioned, if you can be very specific to pulling what you actually need to pull out of the water, rather than just blanketly pulling out anything that will actually bind to it, it does provide that greater cost effectiveness in operation, because you don't have to be constantly replacing or regenerating your resin. Next slide. So now I'll get a bit into the challenges. So I've been talking about, different emerging and proven technologies. So this is just a bit of a snapshot of, I guess, which ones are proven, which ones will actually work. So I did mention dissolved air flotation. Dissolved air flotation is quite common in traditional drinking water treatment, but unfortunately it doesn't work that well on PFAS. But I think the idea being that, if it's already at a plant, then I guess you can leverage that to some extent if if the PFAS risk is high enough. Reverse osmosis, activated carbon, ion exchange, those sort of big three that I had on the first slide. We know they work, and they're quite proven. And then we have some of our more experimental emerging technologies there. Next slide. Something that I think is another sort of hot topic regionally is the, without even putting PFAS into the mix, the issue around resourcing restraints in the water industry is quite a big one. So when you do put PFAS into the mix and then having to have yet another treatment process which is specific for a specific type of contaminant, then you're adding to that strain on your water providers and your operators of your plant. So as I mentioned, dissolved air flotation, activated carbon, two traditional drinking water treatment processes. If you've already got those at your plant, I guess you're halfway there to mitigating the risk. But again, dissolved air flotation doesn't work so well, so don't bank on that one. But then you've got some of your more emerging technologies, and I think the more emerging, the less common technologies or process units are in traditional drinking water treatment. Obviously, the more complex, the more training required for your existing operators. I guess more training means more money. So it's kind of that compounding of that challenge. So that's to mitigate that PFAS risk. Next slide. Oh, that doesn't look good. So I just want to throw this one out there. So I'm thinking, and don't come at me, suppliers, but is there a way we can do things a bit differently? We have utilities, we have water providers who have this hazard. They have PFAS in their drinking water source. We have a lot of emerging technologies that I just mentioned. Is there a way that there can be some sort of mutually beneficial arrangement? So we have technologies that might need to be sort of validated at they're fine at bench scale, they work at bench scale, pilot scale, but there still needs to be some full scale validation. Is there a way that these technologies can be validated at a place where there is actually a risk that needs to be mitigated, and save some money for the water utility, get some have some papers written and have some proven technologies? And this is just my idea, but I think this is one to think about, because I feel like cost, resourcing, I guess the fact that technology is evolving so quickly in this space. I think these are challenges that are they're challenges for non-regional utilities. So I think it's even more of an issue of importance to our regional water providers. So I'm just going to leave it there.
Awesome. Thank you very much, Sally. Okay. Oops. Sorry, can we go next slide, Peter? How's everyone feeling? That wasn't a rhetorical question. So we've now got about 25 minutes for questions for our speakers. So I've got Peter up here. I'm going to ask questions of our three presenters, Jason, Stuart, and Sally. You can tell it's late because I nearly forgot everyone's names. If anyone's got a thought, feel free to use the QR code to ask a question. I had a thought once, but it died of loneliness, but we'll leave it at that. I've got the first question here, and this will be aimed at Stuart. How much did the PFAS blood test cost?
I can tell you from here, can I? So,
yeah, you can say from there. Yeah,
it's $500. So if you know the right people that work in analytical labs, you can get it done free. So I found out later, a number of people said I could have done that for you for free. But the commercial cost is practically $500 through EnviroLab.
I was going to say, is there a particular place that you go? Is it one company or is it a particular kind of specialty?
I only know of one, and they're organising it through a pathologist. So you go to the pathologist,
Yep.
you take your sample, and then they send it off to the analytical
Dr.
facility.
Brad Clark in Victoria.
Yeah.
Volunteered to be a.
So actually, Brad Clark, I saw him speak just this week, and Brad's actually looking at some of the new emerging PFAS in his own blood and finding them. So some of the really unusual next-gen PFAS, he's detecting in his own blood now.
But before we all get scared, the last 14 years, the legacy compounds have been decreasing. So
Yeah.
it's not that bad.
Sorry to be painful. Do you mind, if, Sally and Stuart, if you head to the front, probably just in these two chairs, just so you're visible on the camera? So I've got the little voice in my ear telling me things. Sweet.
So Peter,
Next,
okay.
sorry. So the next question I've got here from the Taree Hub, and this looks like it's aimed at Jason. What is the typical water age in the various layers of the aquifer that supply the Wagga network?
Well, that's a ripper of a question. I don't know. Only by observation, which is probably answering your question indirectly, that it was about 6 to 7 months when I saw the effects of the floods of 2012 actually affect the monitoring balls. So that's probably the only thing I can offer to that question. I'm sorry.
No, that's right. That's right. Next question's for you as well, Jason. What level of the responsibility have the RAF taken for the PFAS contamination? Are they funding any works required to ensure safe drinking water?
I'll have to honestly say that they've been quite honourable. They went front and centre, acknowledged the issues nationally, and they did things very thoroughly, even with an auditor behind them, with all the various meetings we had from 2017. It's to a stage now that they're based on their PFAS, their PMAP, their management plan, with the data they had. I suspect they're being pretty quiet right now, but I suspect they're in this investigation phase of now testing to a very low threshold and doing a reset with all their plans. At the same time, that PFAS is been identified everywhere. It's not coming from the RAF base. So to answer that question more directly, we have started communications with them and getting a clear understanding that if our East Wagga Ballfields is affected, we're expecting them to assist us in terms of what are the options we have at the table to undo that effect.
Sweet. Thank you for that. I think this is for Sally. While treatment can remove PFAS from drinking water, how will the waste streams be managed?
Yeah, I didn't want to go into that.
Well, no, I was going to say that's actually really interesting because just from my perspective, PFAS is being found in a lot of things. So it's one thing to kind of remove it, but then where do you put that waste?
Exactly. It's like finding it, you find it, and you've got to remove it, but then what do you do with it? It's like, I mean, as I said, there are a range of different things you can do to dispose of it, whether you destroy it, or whether you... Destroying it, obviously, is the way that you will not spread the contamination. But, yeah, I think this is the space where I think the technology needs to really step up and because, as I said, incineration is the only surefire, like pun intended, way of destroying it. But yeah, it's like, for example, if you had a brine string from your RO, like, you can't set fire to that.
I'd like to see someone try, but yeah.
So yeah, it's I think it's a whole nother problem in itself.
Okay. No, that's good. I've got one here for Stuart because I think this one could be interesting. Proposed NHMRC guidelines only place limits on 4 PFAS compounds. Are utilities better off not knowing about the occurrence of the other 10,000?
So we don't know about them, right? We don't know the identity of all of those chemicals. We certainly don't know anything enough about the toxicity to be concerned. But we do know that those that are in current guidelines and proposed for future guidelines are the ones that we know the most about toxicity. They are the ones for which the toxicological concerns have driven down to the low levels of assumed safety. So yeah, it'd be lovely for some people to have guidelines for every single chemical known to humankind, but we don't. There's prioritization, and we focus on those that are the higher risk.
Okay. Which kind of gets into that same, almost like what do you do with the PFAS afterwards? Like it's all right to focus on all, but what happens with the rest?
No, that's right, and even incineration. Are we just transferring a liquid waste problem into an air pollution problem? So it's a real problem. We don't have a completely sustainable, satisfactory solution for dealing with these contaminants, even after we've successfully treated drinking water.
Next one I've got here, I'm not quite sure, so I'll throw it out to everyone. How do we confirm high PFAS results reflect actual contamination and not lab error or sampling error, especially with aging or previously remediated assets? So I guess that comes down to accuracy.
Labs don't make any errors. We have uncertainty of measurement.
Well, I mean, even what's the limit for measuring for testing PFAS? I think it's like 2 nanograms.
So that's the problem, is that where we're setting guideline levels now and expecting treatment to achieve is getting down close to limits of detection. And when you get close to limits of detection, that is when you get false positives. That's when you get into the noise, and it's harder to be confident that you're seeing what you think you're seeing.
Yeah.
If I may add to that, we're for the long haul. It's actually getting benchmarking the data, and over time see the trends, and not to overreact on the immediate anomalies. So we had easily, for example, a number of years of data for especially with the RAF base. But because of that reset I mentioned earlier, going now testing to a lower threshold, all that base data is sort of had to just put a freeze on it and start a benchmarking exercise. So and you just have to do that statistical analysis. And take into account that it's going to jump up and down. But you just got to see, is it predominantly above the line or below the line is an indication.
Yeah. No, sweet. I've got a question here for Sally, and you may find it interesting or you may squirm a little bit. What are the features of your ideal PFAS treatment technology? What are the considerations you think researchers tend to neglect?
PFAS.
Well, I mean, that one I was going to read it. That could either be what would be your perfect treatment plan, or what would be perfect, almost, I imagine ideal PFAS treatment's almost like it gets rid of it without having to produce
You've got
waste.
super specific way of only removing PFAS, so you don't have to, because I think what we're seeing now when we're in that planning space, which I sit in, is it's not just PFAS you have to get rid of first. You need to get rid of, essentially have almost an organic free water supply going into your PFAS treatment system. So it's you're sort of potentially spending money where you don't need to, because you don't have to get your organics down that low, and then to do the PFAS treatment. So if you had a more specific way of just removing PFAS, I guess that's perfection, right?
Okay, can I add?
Yeah.
So I mean, really, if you're going to pull all the things together, you'd be low capex, low opex, low skills to operate, complete removal of PFAS. We no waste disposal required, operated by unicorns.
Just out of curiosity, the unicorn is the most likely thing.
Right.
Did you want to add, Jason? Or are you wondering where you can get a unicorn from?
I don't know.
Just to clarify, are you still there, Jason, or you went silent on us?
Gobsmacked.
He's gobsmacked. Did you have any thoughts on it, Jason?
No,
He's on the way.
I can't.
Yes, you had a comment?
I can't add to that. I'm sorry.
Trevor,
Okay.
Trevor,
No, that's right. You hadn't.
would you mind if
Yeah. Yep.
I'm here in Auckland, listening to this conversation. It's very interesting. I am a Kiwi, but I've been spending most of my practice in the United States, and I came back to look at the PFAS situation here, and also to investigate what's going on in Australia. And can I just make a few comments? I notice from Stuart's comment that there's no safe level of exposure for cancer toxicity. Jason mentioned bore levels in Wagga Wagga and Takata, which are way too high. And Sally also said that there's no cheap way to mitigate the PFAS risk. And I just wondered what the Australian water utility companies are going to do about the cost of doing this. This is going to be expensive. And when people, including mothers and fathers, discover that the water that their children is drinking has got PFAS in it, they're going to become very concerned. And I think this will ultimately lead to litigation. So I asked a question in the chat box, which you haven't gotten to yet, but was this: what measures are water utilities taking to protect themselves from liability? And have they looked at what occurred in the United States, where there was a major water supply company settlement against some of the companies who are primarily responsible for contamination? And in the interest of full disclosure, I happen to be a lawyer, so I know that you probably don't want to get into litigation. Nobody wants to go there, but I think it's going to happen, and it's already happening in Australia, in which one of the law firms is suing for personal injuries as a result of PFAS contamination. So those are my questions to any one or other of the presenters. Thank you.
Sure. I might have first pass of trying to answer this question. In terms of liability, if we meet what the New South Wales Health Department expects us to meet, and that's the Australian Drinking Water Guidelines, and ensure that we are meeting that, with our risk matrix I had on the screen earlier, there's no way that we will actually release any water that does not meet the limits, safe limits for drinking water in the Australian guidelines. We just won't. We'll start implementing demand management if we had to, or look for alternative sources. And we just wouldn't go there. Our whole response is built on that. And but yeah, it's certainly a valid question. If you didn't have that assurances of making sure that you are managing your water supply system to the Australian Drinking Water Guidelines, basically.
Yeah, but what about the cost? I mean, look at Jason's situation. He's got bores that are well in excess of the acceptable limits, even for the proposed guidelines. So who's going to pay for equipment that removes this contamination? And, I know that the Sydney situation that Sally's probably aware of, where they've got PFAS contamination that's above the guidelines. So, how are you going to cover the costs of this? And this is not just this year. This is going to be a decades-long process.
Yep. Good question. There's a few steps that it's not capital intensive, and dilution is the methodology we chose first up. With our 2 bores in West Wagga, for example, being twice over the limit, if we're able to get a dilution factor of at least 2, we go below the Australian Drinking Water Guidelines.
Who's going to pay? Jason, my question is, who's going to pay? Are you going to recover these costs from the polluters, or are you going to pass these costs on to the taxpayers?
Well, at the immediate response of dilution, there's really no capital cost. It's a change in operation.
Okay.
But it will get to a time where that only gets you so far as the water demands increase over time, population growth.
Yeah.
By that time, we're hoping that the technologies will emerge, it become more economical, other options to consider, gives us more time to investigate other sources of water that is not PFAS contaminated. So this process of dilution buys us time, and we meet the Australian Drinking Water Guidelines.
Okay, thank you.
Sorry, we've got a question here, yes?
Yeah, we don't batch water. It's continuous production. So we have rear vision data coming back in terms of our verification monitoring. So water's already gone to the customer, and then you get the results back for something like PFAS. We haven't got, as far as I know, we haven't got online monitoring for PFAS. So you only get the results back after it's gone to the customer.
Yeah.
Anyone
want to comment?
The risks are associated with long-term exposure, though, to dose and volume component.
Yeah. Anyone else want to comment on that?
Yeah, if I may, a good example in terms of New South Wales Health, the fact that we were over and several other water supplies were over the proposed limits, that was quite acceptable given that we're below the current limits. And I think someone I heard in the background is that long-term exposure issue. Okay, so we are testing monthly, and it takes about 8 to 9 days before we get the results. Okay, and that seems to be quite acceptable with our regulators, given that it's not a chronic immediate issue, it's a long-term exposure.
Either other two speakers wanted to add comment? Don't have to.
I agree with that point. I mean, that's the way we regulate and we risk assess chronic risks from chemicals. If you look in the Australian Drinking Water Guidelines, many of the chemical contaminants actually explicitly say short-term excursions above the guideline value shouldn't be interpreted as an appreciable risk to human health.
Yep.
It's what happens over the 70-year. When the guidelines are calculated, they're calculated on the basis of 70 years of exposure. So it's really that 70-year average is where the line is.
Okay. No worries.
I suppose just to add, I think there was a part of that question around, how do you, what if it pops up somewhere else? How do you plan for it? What's the sort of, and I think it was in Jason's presentation. So I think it's a part of like monitoring the technologies, sort of having an idea of if it did happen, what would you do, and just I guess making sure that you've got a plan in place and monitoring those technologies and advances in the technologies, so that by the time you actually do it, there'll be a trigger point involved that you go, no, we have to put something into action now, and at that point you hopefully will be a cost-effective way available that you can actually use it.
Got an interesting. Sorry, we'll move on to another question because I think this kind of touches on the same point. It's for Jason, but again, if other speakers want to add comment afterwards as well, how are your customers reacting to these findings?
That's a really good question. When there's an upbeat in the media, there's a few more inquiries that we get, and some of those inquiries are superficial, or and some are actually quite deep intellectually. Overall, I think our customers are quite apathetic right now. We have a fair bit in our trust bank, and we pride ourselves with that. The safety of our water supply is number one. We won't compromise, and we haven't seen much indication where they doubt us on that, nor should they. We're part of the community. Our families are drinking the same water. So I think we're running on that goodwill. The real test, I suppose, is what is going to happen with Tarcutta when they are actually impacted, not by the safety of water, by the limited supply during a drought or during summer conditions where we're down to one bore, and hopefully that bore stays below the drinking water limits. But saying that, it has higher iron, which means more backwashing, which means less production. So when our customers are in fact impacted, Again, not by water quality, but by us putting water restrictions on, because we can't maintain production until we find an alternative to supply. That's when they will start asking questions more so. We just haven't had that come across that situation yet, but it's just around the corner, no doubt.
All right. Any comments from our other panelists? Sweet. I've got a couple more minutes left. I've got a question here for Stuart. Stuart mentioned that 98% of Australian population has PFAS in their blood. Where do the 2% live?
Measurable PFAS in their blood. So I think you can probably assume that 100% have PFAS in their blood, but there's a curve, and some people just happen to be on the detection limit side of the curve.
No, I'm pretty sure that question was under the definition of facetious. Yeah. So. I guess another question for Stuart and for all of our panelists. Is domestic ingestion of PFAS through cosmetics and non-stick cooking surfaces a larger potential bloodstream source than drinking water?
So that's one of those questions with lots of uncertainty. We know that there are all these different sources out there, including things that we apply to our lips and our skin and put in our mouths. But there's a huge amount of uncertainty in terms of understanding relative exposure to the different sources, and particularly when you start talking about different chemicals. PFAS ain't PFAS. So that's difficult. But when you look at the international agencies have made an attempt to try and quantify it, what the US EPA says, for example, is that unless you're in a very highly contaminated site, and there are highly contaminated sites in the US because of manufacturing of PFAS, probably about 20% comes, we assume, this is an assumption really, about 20% comes from drinking water, 80% from everywhere else. We do know that household dust is a big one, and we know that food packaging is a big one.
And we're right at the limit, but I do have one more question, which I think will kind of touch on that a little bit as well. And I guess it'd be open to all three. I'll probably start with you, Jason, though. How do we collaborate with our friends in the waste/landfill industry on PFAS issues?
Well, if they can actually ensure that there's no PFAS leaching into the groundwater table from historic or current use of refuse sites, that's a good start. And I don't think there's a real active monitoring regime of those tip sites, for example. I think there's still a bit of a blind spot. It's like if we look for it or find it, we have to do something about it type of approach. And that's something that we all have to play a part, because it's not the tip owners, operators' fault why it's there. It's a whole community. It's fault why it's there, and we need to sort of share the pain to contain it, to treat it. It's probably the best answer I could provide. I'm sorry.
No, that's sweet. Other panelists have a comment? I mean, it is an interesting thing in that it's not just drinking water that's got PFAS in it. So
where you look for it, you find it.
Yeah.
And I mean, there's also that piece around, as we've been able to detect lower and lower concentrations and actually detect it.
Yep.
How long have sort of water treatment schemes been operating, and they've got residuals potentially on site? I mean, what do you do with that? Like, it's, I guess these advances in technology are both a help and a hindrance in a way.
So you had a really quick comment?
Yeah, I'd like to make 2 comments. One of them is just to say out loud, ultra short chain PFAS compounds like PFA. It's coming, you guys better look at it and be ready. That's that. And one gift for you, not everybody in the room would know, but illustrious NATA, National Association of Testing Authorities, has made a ruling that TOPA is no longer a determination but a capability. So think about that. Meaning it's no longer an analytical test method, it's just a capability that you can oxidize your sample.
Yep.
What that may mean to you.
No worries. Sweet. We could probably spend all night here, but I'm sure everyone wants to see the origin. So I just wanted to say thank you to everyone for attending. Again, thank you to our 3 fantastic speakers, Stuart, Sally, and Jason. Again, thank you everyone for dealing with the, I'd like to say minor IT issues, but they were a little bit more than minor at some points. Also want to thank our hubs for attending, as well as all the online attendees. I was informed just before the start of this event that, and Richard made it well known from coming in from Auckland, but we've had some attendees from across Australia as well, from different states. So it's definitely a topic that I think is starting to get more and more attention. And I think it's great that we're able to sit here and actually have an honest conversation about PFAS, what it looks like now, and what it's going to look like in the future. So I just want to wrap it up there. Just a couple of quick things to bring up. The water profession is interested. I think there's another 30 tickets left. Just a chance to kind of unwind at the end of the financial year. It's over at the Shelbourne Hotel. And we've also got the state conference on the 18th, 19th, and 20th of August. Shameless plug for the regional champs. We're looking at doing a panel session, looking at the relationship of Indigenous people with water, how it's managed and how it could be managed better. We've got 3 speakers. We've got Jamie Soward as our facilitator. We've got Phil Duncan, Tara Deva, and got to get a third panelist, all Indigenous people telling their stories on their relationship with water, and also going to have a similar panel session as we debate it as well. So if you're interested, there's going to be a lot of other things going on at the conference, but as a shameless plug, we're also looking at running a panel session there as well, which hopefully should be as interesting as fun as tonight's panel session. So if we jump to the next slide, Peter, I think that's it. Just want to say thank you to everyone attending again. Thank you very much for your patience, and we'll wrap it up there. Thank you.
Thank you very much.
Thanks, everybody.
Thank you.
Thank you.
Thanks.
Thank you, legends.
Goodbye.